Okay. So, make sure we're recording. We are. Here we go. So, this is not 122. This is more on ionic compounds. So, we know that molecules form. We're talking about how a molecule forms today. How a molecule forms. So, the way it forms for specifically an ionic compound is called the Born-Haber process. I don't know if I spelled process right, but I think it's close. Let me zoom in a little bit. There we go. So this is essentially saying that atoms, molecules form in multiple steps. They form in multiple steps. So what I'm basing this off of is page 315, but I'm going to explain it to you. So I'm going to make a little chart here. So on this end, I'm going to have energy in kilojoules. So here's energy in kilojoules, increasing. And we're going to talk about all the different steps there are in a reaction. So if I wanted to make lithium fluoride, how would that look? Well, I'm glad you asked. So I have lithium solid, the states really kind of matter, plus 1/2 F2 gas. So I have 1/2 of a fluorine gas molecule. So this is where I am starting on this scale. The first thing I need to do, and this is all the different steps that happen in making a molecule, but it happens like that. But here are the steps that actually happen, is I cannot really do a lot with gaseous fluorine. So the first thing I have to do is I have to take this up a level. So this takes more energy. And I need to change it to this. Now I would have lithium gas plus 1/2 of a mole of fluorine solid. Wait a second. Oh, shoot, I messed that up. Sorry. The gas is right. This is staying a gas. I should have said I can't react a solid with the gas, so I need to turn the lithium into a gas. That makes a lot more sense. So I need to turn my lithium solid into lithium gas in order to make these react. And if you change something directly from a solid to a gas, that is called sublimation. So this is going to be the energy of sublimation, which is 161 kilojoules. 161 kilojoules. Okay, so I have them both in gaseous form. Now I need to do something else to it. So the next thing I need to do, and you're never going to have to draw one of these, I'm just kind of showing you all the steps, is I need to ionize my lithium to give this electron away. So now lithium positive. Now I have an ion of lithium plus 1/2 of a fluorine gas. I have now ripped an electron off here, and I'm ready to give it to fluorine. Well, when you ionize something, that's called the ionization energy. And ionization energy for this is going to be 520 kilojoules. Take it up one more level. So the last level, actually there's still 2 more levels. Wait, I've got 1, 2, 3. No, this is the last level. I have my lithium plus gas plus, now I give this ion over to fluorine. This becomes fluorine gas. And now I have bonded my fluorine. I no longer have half of a fluorine gas. I now have a whole fluorine molecule. So that's my bond energy. So now I'm at the top. And you guys can read more about this on all of these. So this is on page 314, 315. Now I need to, am I still on the screen? Yes, I'm still on the screen. Now I need to give fluorine this ion. So now I'm going to have lithium positive gas plus fluorine negative gas. And this is called my energy of electron affinity. This is my electron affinity energy, which is going to be negative 328 kilojoules. Because now I'm starting to bond, so my energy is going back down. And then the last thing that happens is this big jump, and this is my lattice being formed. So this is my lattice energy, which is negative 1,047 kilojoules. Essentially, what this is showing you is the following. So this is saying that my delta H of the reaction is equal to my sublimation energy plus my ionization energy plus my bond energy plus my electron affinity plus the lattice energy. And I know what all of those should add up to, because the difference between here, which is also here, this difference right here, when I subtract those two, it's going to be negative 617 kilojoules. I'll get that same answer by adding up this plus this plus this plus this plus this. So this is my delta H reaction. So this is negative 617, is all of them added up. What are you going to do with something like this? Well, you might see where you have to take your ionization energy and divide it by 2. Or maybe you have to multiply your electron affinity by 2. So all you're going to be doing with this equation is just looking at this and figuring out if you have to divide something or multiply something to get your delta H reaction. If we're going to define lattice energy is, once again, the energy required to separate a mole of an ionic solid into gaseous ions. So if I asked you which one has the higher lattice energy, I could say CAF or MGF. I'll pause, let you guys think about that. Higher lattice energy is going to be MGF. Why? Coulomb's law. Because magnesium is smaller than calcium. Same charges. This is smaller. So it's going to take more energy because there's more attraction to separate a mole of that. So that is lattice energy. Okay. The next thing that you're going to have to be able to calculate is bond energies. This is page 323 in the book. So on page 323, they give you a list of bonds. So page 323 has all of these bonds. So that's my bond energies. So I'm going to give you an equation, something like this. So CH4 plus O2 yields CO2 plus H2O. Step 1, balance it. So I'd have to put a 2 here, 2 there. And I could tell, well, we don't know what our delta H, we need to figure out what is our delta H reaction. So the first thing I like to do is I like to draw this out. So I have C, H, 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 H. I know oxygen is oxygen double bonded to an oxygen, and I have 2 of those. That gives me, we've drawn this out, C double bonded to O, And then water is HOH. And I have 2 of those. So I kind of draw this out because I need to know my number of bonds. Here's the equation. Delta H reaction is equal to the sum of the bond energy of the broken minus the sum of the bond energy of the formed bonds. So you will notice that this is backwards. Because when we were doing delta H reaction, it was products minus reactants. Well, here, the broken ones are here. So for bond energies, it's actually reactants minus products, because I'm breaking these bonds to make bonds over here. So here's how this would look for this equation. Delta H reaction equal to bonds broken. So let's start out with our CH bonds. I have to break 1, 2, 3, 4 of those because I have none of those over here. So all 4 of these bonds have to get broken. So here's my sum. So I have 4 moles of CH bonds times my carbon-hydrogen bond on this page is right here, 413. And that's kilojoules per mole. So it's 413 kilojoules per mole. Plus, I have 2 oxygen double bonds. I have no double bonds on this side. So I'm breaking 2 moles, so plus 2 moles of O double bonded O times O double bonded O is 495 times 495 kilojoules per mole. So there's my bonds broken. I'll show on the screen. Minus bonds formed. So new bonds on this side, I have 2 C double bonded O's formed. So I have 2 moles of C double bonded O times, that's on that page, 799 kilojoules per mole. Plus, I have 4, because I have HO times 2, I have 4 moles of H to O bonds. So this is the ho, 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 ho. That was a Santa joke. Times HO is 467 kilojoules per mole. The sum of that. You will add all of that up. When you do that, you end up with delta H reaction being negative 824 kilojoules. And then this number would go up here, like old chapters, negative 824 kilojoules. So this is an exothermic reaction, which makes sense because this is burning methane. When you burn stuff, it feels hot. When you burn stuff, you release carbon dioxide and water. Exothermic reaction, negative 824 kilojoules. So those are bond energies. Okay. Now, this is going to be our introduction to bonding structures. So this is the start of all of our shapes, bonding, all that stuff. So let's look at CH4. And let's draw the off-ball diagram. But we only need to worry about our outermost electrons. So here's my 2s. Here are my 2p for carbon. Because carbon is the one that is bonding. Carbon is what the hydrogens want to. So carbon, I fill both. I have my 2s filled, and I have a 2p and a 2p. This is what my outermost electrons of carbon look like. So, the problem is, I need to connect 4 electrons from hydrogen. I have to connect 4 electrons to hydrogen, but I only have spots to pair for 2 because I have to pair with a down. So what I have to do is I have to take this 1 electron here and I have to promote it. So I promote this electron right here. Now, this basically isn't here. And now I have 1, 2, 3, 4 electrons waiting to get a pair. So this means I could bring a hydrogen here. I could bring a hydrogen here going down. I could bring a hydrogen here and a hydrogen here. So I can bond a hydrogen at each one of those spots. This is called a hybridized orbital. This is called sp3 hybridized. Why is this sp3 hybridized? Because I hybridize one s and I hybridize 1, 2, 3 p orbitals. So I hybridize my s and 3 of my p's. This is saying where are my hydrogens going to come in and bond? One's going to go at s and 3 are going to go into my p's. Remember, an s orbital is a sphere, a p orbital is a dumbbell. So an sp kind of looks like this, kind of like both. It's kind of like both like that. So if I was going to draw what this would look like, it's sp3 hybridized, so I basically need 4 of these. So it would look something like this. So here would be 1. Here would be 2. Here would be 3. And then this last one is kind of like coming out of the paper at you. Wow, that's a horrible drawing. That is really bad. If I was going to draw it just with, it looked kind of like this. That's still bad. Really bad drawing. But essentially, it's kind of like a triangle with 1 coming up. So this is kind of like a trigonal base. And you're probably thinking, yeah, right. Plus 1 rising. So you can kind of see like the trigonal base here, then 1 coming up, and this would be considered tetrahedral. That probably does not make a lot of sense yet. This is the very, very basic introduction for what we're going to be doing tomorrow. Tomorrow this will make way more sense when I draw this with real molecules. So this hybridization, we're going to come back to this tomorrow. So let's talk Lewis structures. So we had been drawing some of these, but I'm going to officially make this so we know the actual rules for drawing Lewis structures. Step 1. When you're drawing a Lewis structure, you sum your valence electrons. We've been doing this without even thinking about it. Step 2, use a pair of electrons. Remember, these are shared to form bonds. Use a pair of electrons to form bonds. And then step 3, satisfy the octet or duet rule. So let's start out with water. H2O. Water has 1 valence electron times 2 plus oxygen has 6. So I know for water I have to show a total of 8 electrons. Okay. So you usually put the most electronegative thing in the middle if you can't decide, or just what makes sense, which on this one it makes sense to have oxygen in the middle. So oxygen, I have an H here, an H here, so that's 2 4 electrons accounted for. I need to show 8. So I have 2 here and 2 there. So that would be the Lewis structure for water. What about PBr3? Phosphorus, and you can pause and try this on your own. Phosphorus has 5. Bromine has 7 times 3, which is a total of 5 plus 21, 26 electrons. Phosphorus wants electrons more than bromine because of less shielding, or just the individual one. Connect to bromine, connect to bromine, connect to bromine. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 8, 16, 24. I need 26. So that means that this phosphorus is going to get a lone pair. It's going to get a lone pair. So that's PBr3. Here's the problem. The problem is when you get to something like HCN. Hydrogen has 1 valence electron, carbon has 4, nitrogen has 5, for a total of 10 electrons. So I would say pause here and try to draw this on your own. And then I'm going to show you, here's the problem with this. First problem. So, carbon goes in the middle here, because carbon is kind of like the one that has 4 bonding sites, so it would go in the middle. If I connect carbon to nitrogen, carbon to hydrogen, hydrogen's happy because it has a full outer shell with 2. I give 2, 4, 6 to nitrogen. Nitrogen's happy, 2, 4, 6, 8. Hydrogen's happy with 2. The problem is carbon only has 2, 4. That won't work. Okay, well, what if I try putting 2 on carbon in the middle? Carbon, 1, 2, 1, 2. Okay, so I have 2, 4, 6, 8. So carbon's happy. I put here for my 10. Hydrogen's happy, carbon's happy. Now nitrogen's not happy. That won't work. What if we try a double bond? I can't double bond to hydrogen because that won't work. What if I double bond to nitrogen? 2, 4, 6, 8, 10. That's good. Hydrogen's happy. Nitrogen's happy. Carbon only has 6. That won't work. So for this one, I have to do hydrogen, carbon, triple bonded nitrogen with 1 lone pair. Hydrogen has 2. Carbon has 2, 4, 6, 8. Nitrogen has 8. Everyone's happy. So you have to watch out for things that could have multiple possibilities, which I'm going to show you in a second how to do that. Here's your exceptions, because once again, there's lies. The exceptions to the octet rule. First of all, boron. So if I had something like BH3, boron has 3 valence electrons, 3 hydrogens have 3 for a total of 6 electrons. This would look something like this, BHH. I only have 6 valence electrons. I only have 6 valence electrons, so that's done. So this is less than 8 possible. That's less than 8. And then if you look at sulfur, it does something like SF4. So sulfur has 6 valence electrons. Fluorine has 7 times 4. Excuse me. Which is 28 electrons. So this is a total of 34 electrons. So if I draw this one, I do my sulfur with an F, an F, an F, an F, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. I mean, here's 2. So that's 8, 16, 24, 32. I need 34. So on this one, I have to draw a lone pair on sulfur. So sulfur has an expanded octet. So essentially, The exceptions to the octet rule are BS. That was a joke. So basically, what I'm saying is that Li or Be or B can have less than 8. From carbon to silicon, you have to have 8. And then phosphorus and past can have greater than 8. So carbon and silicon are truly the only ones that will always have 8. It will always have 8. Okay. So let's say I had something like this. NO3 minus 1. Lewis structure. Well, nitrogen's 5. Oxygen's going to be 18. A negative 1 must mean I gained an electron for a total of 24 electrons. How would this look? Well, nitrogen in the middle. Oxygen, oxygen, oxygen. I need 24 electrons. I know if I would just put 888, nitrogen's not going to be happy. So I'm going to have to put a double bond here. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Everyone's happy. And usually put this in a bracket with a -1 charge whenever you're drawing an ion. Here's the thing. I could also draw this like this. Nitrogen double bonded to oxygen, single bond, or I could draw nitrogen double bonded to this oxygen, single bond. I didn't draw my lone pairs. But you can see the double bond could be here, or it could be here. This is called resonance. This is called resonance. Resonance is more than one possible Lewis structure. More than one possible Lewis structure. So, how might I draw this? You might draw it like this. So here's my N, here's my O, an O, and an O. And you can draw dots to say that that double bond can go anywhere. The double bond can go anywhere. And actually it kind of rotates. It doesn't just stay on one, it just kind of goes in between. This is an organic molecule. 1, 2, 3, 4, 5, 6. This is called benzene. So benzene has 3 double bonds. And these double bonds can actually rotate. So they can go here, 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 here. Sometimes you'll see benzene drawn like this with just a circle in the middle because those bonds are always moving. So that's the resonance structure for benzene. Kind of a hexagon with a ring in the middle. So resonance is more than one possible Lewis structure. Okay, we're still rolling. How many minutes are we at? 28. Okay, perfect, because I wanted to go 40. Okay, moving on. The last thing, so we have these resonance structures. So if more than one is possible, how do we know which one is right? Well, I'm glad you asked. The way we know which one is right is by using formal charge. So this is used to evaluate non-equivalent Lewis structures. So it's used to evaluate non-equivalent Lewis structures. So there is a couple goals that we have with formal charge. Goal number 1 is to have the lowest possible or 0 formal charge overall. So that's goal number 1. Goal number 2, any negative formal charge. So if I have to end up with a negative, it should be on the most electronegative atom. Should be on the most electronegative atom. And there's a little equation for calculating formal charge. Formal charge is equal to the difference between valence and electrons and atom owns. Put owns in quotations with little asterisks. Here's the asterisk. The asterisk is you only own half of each shared bond. So an atom owns all of its lone pairs, but of the dashes it only owns half of each shared bond. So here we go. Let's look at POCl3. Phosphorus has 5 valence electrons, oxygen 6, chlorine 7 times 3 is 21. 5 plus 6 plus 21 is a total of 32 electrons. So on this one, I'm just going to tell you, phosphorus has to go in the middle. So phosphorus, chlorine, and you're not going to be responsible for drawing these, like figuring out which one goes in the middle. You're just going to have to tell me like formal charge or something like that. So I need 32. So all of these are going to have all the lone pairs. 8, here's 6 plus 2 is 8. 8, 16, 24, 32, 32. So the formal charge for each one of these. Phosphorus's formal charge. So we said it's a difference between valence electrons and what it owns. Phosphorus has 5 valence electrons from the periodic table. Minus, how many does it own? Well, it has 4 bonds attached to it. So it has 2, 4, 6, 8. But it only owns half of each one of those. So it actually only owns 4 electrons. So 5 minus 4, phosphorus has a formal charge of 1. Oxygen, on the periodic table, it has 6 valence electrons. Minus how many it owns? It owns 2, 4, 6. One of this pair, so it owns 7. So 6 minus 7 is negative 1. And then chlorine has 7 valence electrons on the periodic table. Minus it owns 2, 4, 6. One of these, 7. So 7 minus 7 is 0 for all the chlorines. If I add those up, 1 plus negative 1 plus 0, that is 0, meaning this is a good Lewis structure. So, a couple other things you might see, and that's it for formal charge. So, the sum of formal charges is equal to the overall charge of the compound. That's the first star. Second star, 2 bonded atoms can't have the same sign. So phosphorus, right? And oxygen, positive, negative. Positive, 0. Can't have the same sign. And then lastly, here's the kicker. Here's what we're going to do with this. If 2 or more Lewis structures exist, comma, that means resonance, choose the one with the lowest formal charge. What do I mean by that? carbon dioxide. So carbon dioxide, I could draw it one of two ways. I could draw it like this. Carbon, oxygen, triple bond oxygen. And then this one could get 1, 2, 3, 4, 5, 6. I need 4 plus 12. I need a total of 16. This one has 2, 4, 6, 8, 10, 12, 14, 16. Oxygen happy, carbon happy, oxygen happy. Or I could draw like this. 1, 2, 3, 4. 1, 2, 3, 4. Oxygen happy, carbon happy, oxygen happy. So now I have to look at the formal charges to see which one's better. So over here, oxygen has 6 valence electrons, minus, it owns 2 plus 1, 2, 3. 6 minus 5 is plus 1. Carbon has 4 valence electrons, minus, it owns half of these. So 4 minus 4 is 0. This oxygen has 6 valence electrons, minus it owns 2, 4, 6, 7. This oxygen is a minus 1. Overall charge 0. That's pretty good. Could be this one. But over here, this oxygen has 6 valence electrons, minus 2, 4, 5, 6. Formal charge 0. Same as the other carbon, 0. This one, same as that oxygen, 0. So while these both add up to 0 overall, this one has 0 on every single atom. So this is the correct formal charge, the correct Lewis structure. My hand hurts, which means your hand probably hurts. So that is good for a Monday. Tomorrow, we will start Vesper. Nice work.